Well, here's our final installment of Lecture 6. We're going to look at how different types of bonds might form between two atoms. And in order to look at that, one of the properties that we have to look at is something that is called electronegativity. Now, electronegativity is sometimes abbreviated EN, so if you just see EN in my slides, it means electronegativity. Now, electronegativity is a man-made value. It doesn't really have a physical measurement. So in other words, you cannot go out to the store and buy an electronegativity meter. It has to do with different measurements that were made between lots of different compounds, and comparisons were made. There's lots of different formulas used to try to calculate the electronegativity, and then they get signed with an arbitrary value that has some set maximum, and everything gets worked on from there. We don't need to worry about the formulas. So again, it's a theoretical value only. It's all we wanted to mention. Now, what is electronegativity? Well, it has to do with when two atoms form a bond between them, and it's the one element's ability to pull the electrons shared in a bond towards itself. I like to think of it in terms of if you have two people sharing a blanket, one of them might be more of a blanket hog, and that person would be the equivalent of a very electronegative atom. So the more electronegative an atom is, the more it wants to pull shared electrons towards itself within a bond. And so in general, as you look at the periodic table, electronegativity increases as you move up and to the right in the table. Because we're looking at the effect of two atoms in a bond, we don't look at the electronegativity values of the noble gases, because they don't form bonds very often with other elements. So if we ignore helium because we have no known helium compounds, fluorine is the most electronegative atom we have, and the most common set of values we use to assign electronegativity. Fluorine would have a value of 4.0. So we can look at a table of what that's going to look like here in just a little bit. So what do we do with electronegativity? Well, in addition to being able to figure out what type of bond we're dealing with, it also helps us establish kind of a standard with how we write chemical formulas, or figure out how certain molecules are structured. So generally, when we're writing a chemical formula, the least electronegative atom goes first. This is why in ionic compounds the metal is generally listed first, because it's the least electronegative. And also generally, when you have a structure with a central atom, the least electronegative atom is usually right in the center there. So let's look at a table of electronegativities here. This the periodic table kind of tilted here. We can see we really have a lot of differences in electronegativity. Hydrogen's kind of an outlier way over here. It has a very high electronegativity for where it is compared to the rest of the group 1A elements along in here. You can see, though, that as you move up the periodic table, you do have a general trend of increase in electronegativity. We see that also over here with the halogens, with the group 6 elements, the group 5 elements. And then as you move from left to right, you also see a general increase in electronegativity. You do see some weird things happening here with the transition metals. That's okay. We don't need to worry about them too much. They don't pop up very often in these types of determinations. For electronegativity values, a lot of times we'll use these elements here, your main group elements, so groups 1 and 2, and then all of these over here, groups 3 through 7. So you can see here we've got fluorine at a 4.0, nitrogen at a 3.0, oxygen at 3.5, chlorine at 3.0. Notice that these elements are the only ones that are 3 and above, nitrogen, oxygen, fluorine, and chlorine. A lot of times we call them the electron hogs. So if anything is attached to them, usually the electrons that are shared spend an awful lot of time around these atoms, and not very much time around the other atoms. So one of the consequences of electronegativity is something that's called a dipole moment. And so this is a measurement of the charge separation in a molecule. And that charge separation is caused by the electrons in a shared bond spending more time around one atom than they do around a different atom. And so that dipole moment is affected by something called the polarity of the bonds, and that polarity is caused by a difference in electronegativity. So remember, if you have two atoms connected to each other, if one of them is more electronegative, the electrons within that bond are going to be pulled closer to the more electronegative atom, and they're going to spend more time in the orbitals around the more electronegative atom than they do around the less electronegative atom. So here's kind of a result of that type of interaction. So you can see these little deltas here. So if we have two atoms here, we've got a hydrogen and a fluorine. Hydrogen had an electronegativity of 2.1. Fluorine had an electronegativity of 4.0. So there's a pretty sizable difference between those two. So what that means is that the fluorine has the electrons around it more often than it does around the hydrogen. And so it gets a partial negative charge, and that's what that little lowercase delta means, delta minus. So it has a partial negative charge. It's not a full negative charge like you would see in an ion. It's still a shared bond between these two, a covalent bond there. But it does have just a partial negative charge, and your hydrogen has a corresponding partial positive charge. Now, if you put those kinds of molecules in an electric field, there's obviously no effect. They're randomly oriented. However, if you turn the electric field on, you do see an orientation of the molecules with the dipoles here pointing towards their opposite charge. So your hydrogens with their delta plus are going to point towards the minus plate of the electric field, and the fluorines with their partial minus charge are going to point towards the positive plate in the electric field. So they do align within the electric field. So we mentioned that the separation of charge leads to a dipole. If you have molecules that have a net dipole, we say that they are polar. If you have shared electrons between two atoms, then you have a covalent bond. And if that covalent bond has that difference in electronegativity, then we say that that bond is polar covalent. And if a bond is polar covalent, it's going to have that delta minus and that little delta plus. Okay, if the difference in electronegativity or separation of charge is large, so in other words that delta En is greater than 1.7, so that's what we actually use in our book is 1.7. You'll see different values in different books. I've seen books use 1.8, I've seen books use 2.0. That range between 1.7 and 2.0 is very much a gray area as far as what type of bond forms. But for our purposes, if the difference of electronegativity is greater than 1.7, then we say that that bond is ionic. In other words, the time that the electron spends around the more electronegative atom is so great that for all intents and purposes, we say that that electron has been transferred to that more electronegative atom, and that has formed an ion, an ionic compound. So if we have a delta En that is very small, then that bond would be nonpolar, and usually for nonpolar we say that that's between 0 and 0.4, or covalent. That's the same thing actually. So nonpolar and covalent are the same thing. Okay, so you can have this polar covalent. I missed this. I apologize for this. So for polar covalent, that delta En is going to be generally between 0.4 and 1.7 for the delta En. So here's a table listing these. Again, this comes out of a different book, so I'm going to change those numbers. This is just a nice graph. That's why I like to use it. So it's going to be 0.4 to 1.7, and we're going to say that's 1.7 plus. Okay, so examples where the electronegativity is very small is when you have the exact same two atoms bonded together, so chlorine molecule, Cl2. The difference in electronegativity there would be 0 because the two atoms are exactly the same. So you can think of it as a tug-of-war. They pull with the exact same strength. With HCl, I'm not quite sure what the difference in electronegativity there is. I want to say it's 0.9. If I remember right, it's close to that. So that falls in that range between 0.4 and 1.7. So that bond is going to be polar covalent. And for ionic, you have sodium chloride. I do not know what that difference is off the top of my head. We'll say it's 2.2, just as an example. So that's greater than 1.7, and so that would be ionic. And so again, let's change a number here in this little table. Again, I like this table, but it comes from a different book. So if we change that to 1.7, so here between 0.0 and 0.4, the difference in electronegativity is fairly small, and so we say that those electrons are shared equally. Between 0.4 and 1.7, those electrons are being shared, but they are not being shared equally. It's kind of like when if one of your little siblings, younger siblings, wants a piece of your candy bar. You don't give them half the candy bar that you have. You probably break off the smallest piece you can and give them a piece there. Technically, you shared your chocolate, but you did not share it equally. That makes you a polar covalent bond. So, polar covalent bond. Sharing happens, but does not occur equally. Notice for polar covalent, we have the delta minus around the more electronegative atom, delta plus around the less electronegative. And then here, if that difference is greater than 1.7, then we say that the electron has been transferred, and you get a full negative charge and a full positive charge. So here's some examples that we can try. So iodine and iodine. So we have two of the exact same elements there, and so the difference in electronegativity is going to be 0. And if the electronegativity difference is 0, then we have a covalent bond. Okay. How about cesium and bromine? So we have cesium here at 0.8. We have bromine at 2.8, and so that's going to be 2.8. To find the difference, we take the larger number, 2.8, minus the smaller number, minus 0.8. That's equal to 2.0, and that is going to be ionic because it's greater than 1.7. And if we look at phosphorus and oxygen, so phosphorus is here at a 2.1. Oxygen is here at 3.5, so we have 3.5 minus 2.1, that's equal to 1.4, and so that is going to be polar covalent. So when you're looking at the type of bond, you're just looking between two individual atoms. So if you're looking at the types of bond present in an entire molecule, you want to identify each individual bond just between two atoms. You don't add up like all of the phosphoruses and all of the oxygens and multiply them together and subtract them. You're only looking at a single bond between two atoms, so you only look at those two atom types. Now, that having been said, especially with the ionic bonds where we say the electron has essentially been transferred, something to remember is that virtually all bonds have some covalent character. So even though we have a large electronegativity difference, there's still going to be some sharing truly taking place. We just use that label of ionic to help us understand what's going to happen with that electron and where it spends most of its time. So because of that, we have something that's called percent ionic character, which basically looks at what percent is ionic and what percent is covalent. So it's an important concept to keep in mind. There is a calculation involved in calculating the percent ionic character. It's not something that we do in this course, but it is important to understand the idea that even for an ionic bond, there's still some sharing taking place. But we are not going to do any of those calculations, but you do want to make sure that you understand the concept of percent ionic character. All right, well, that finishes out all of our parts in Lecture 1. If any of those parts don't make sense to you, or if you have questions, you are always welcome to contact me either through email, or if you're on campus, you can certainly stop by my office to see if I'm there. Best of luck to you, and we will see you in Lecture 2.